Hello and welcome to Data with Tom. Today we're focused on using dynamic tables with machine learning models. And this is a really cool functionality because you're able to do incremental refreshes of your table, of your dynamic table, and incremental predictions with your machine learning model, all in a very automatic and managed way, just by creating a dynamic table. So we're gonna walk through a notebook that's made available by someone on the Snowflake team, a publicly available notebook. We'll load that in and create these objects. So first we're gonna train a model on the Titanic data set, an XGBoost model, and we're gonna save that to the model registry. And then we're going to execute this create dynamic table where we create the dynamic table which draws from the base data, does some transformations to kind of turn the columns into the data types that the model is expecting. And then you can see right here, it runs the predict function, loading the model and running the inference on those base records, you could say. So incremental predictions at every 1 minute. And if there are no new records, then the model won't be loaded, it won't execute a refresh. But if there are new records, at every minute, it will execute those inferences. So this is great for batch predictions where you have data coming in at kind of a set schedule. This is not for online inference where there are continuously new data points like that you need inference run on them immediately. You know, there's a different solutions for that. That can be a whole nother video. So let's get into the actual code. We're going to open up our trial account on Snowflake. And let me actually change the appearance here. I'll make it light. So we're going to go into we're going to go into notebooks. And the way that we're going to do this, we're going to create a notebook from a Git repository. We're going to clone it from a Git repository. And let's see, the way that we're going to do this is clone this repository from here. We're going to go to this repository made available by a Snowflake employee, Chase Romano. He's awesome. He puts out a lot of great content. So let's copy this URL, paste that in, Snow.ds training, I'll call this trial account. We don't need an integration here because this is publicly available. Oh, but I guess it says we do need one. Okay. Yeah, create Git repository. Trial. Okay, so first, all right. So first we will need to follow these setup scripts. This is really the only thing we need to do right here because we're accessing a public Git repository. So yeah, copy this code, just this first block right here where we're creating an API integration. So let's cancel out all of this. Let's go into workspaces. This is kind of the new way to edit SQL in Snowflake. We'll just create a SQL file called setup and then make sure we're account admin and execute this code. So now we have a Git integration. What this allows us to do is, this basically tells the Snowflake platform, hey, it's okay for me to access GitHub via Snowflake. You know, don't block that. It's okay for that to happen. So that's all that's happening there. To role account admin. Okay. Let's say show API integrations. Git integration external API enabled true. Okay, so hopefully that works. Let's refresh this page. Create from repository. Again, I need to go back and copy this. URL. Okay, there we go. Git integration. And it is a public repository. So now let's put this into our learning DB. Public schema is fine. And I click create. Awesome. So once we have created the Git repository, we can now navigate into the MLOps folder, and then we're going to be doing that 101 batch inference. Like I talked about before, this use case is really meant for when there are when you're not doing online inference, when it's like, you know, you want to perform inference across 100 or 1,000 or 10,000 records at a time. This online inference, this is another video that I'll probably make soon. That's where you can actually hit an inference endpoint, much like you would in SageMaker or Azure, where the model is sitting kind of hot, ready to go on a compute instance somewhere in the cloud, and you can very, very quickly, with sub-second latency, get predictions back. So we're going to stick with the batch inference for today, and then we'll click on this batch inference notebook. The great thing about the way we're doing this today is that it's going to load in the sample data, and it'll just run, the notebook will run top down, and we don't have to mess with it like loading in data or anything. So we'll just call this batch inference video notebook. Cool. And we're going to run this on a container because we're going to be doing working with open source libraries like XGBoost and pandas to train this model. And everything else we can keep standard. And yeah, we're following what this tip is saying. Running ML, do container runtime. So containers take a little bit longer to start running, so let's just click start to get that going, because it's pretty much initializing an entire Kubernetes container for us to run on. We're using the standard like default compute pool or compute instance for the container runtime, so it's extra small. It burns like less than a credit per hour or something, so it's very cheap. We can see in our environment here we have the data loaded in, the Titanic Snowflake CSV already, so we don't have to mess around with bringing in any data. And let's just read through this. So we have an overview where we're going to start by ingesting data from Snowflake. Well, there's actually step 0 is turn this CSV into a table in Snowflake. And then we're going to pull the structured data from Snowflake into memory, do some feature engineering, transforming it with like doing some dummy encoding. We'll train an XGBoost model. We'll then register that to the model registry, and then we will call the model to make predictions via a dynamic table. So this here is just to show that if you wanted to, you could pip install these into the container, but these already come pre-installed in the runtime. I think these don't show automatically here, but if you wanted to, like, yeah. So there are no packages that I personally have added, but the container runtime comes preloaded with a ton of different open source libraries already. So let's just hit run all. And we can see we're loading in Streamlit, Pandas, scikit-learn, XGBoost, Snowflake packages to load in the model registry, and then Snowpark for getting the active session. So we create a session that allows us to connect to our Snowflake instance. I'll close that up. We can see here on the right that we're, it's going down the list of cells to execute. And I'm not going to go as much through like the data science techniques here. We're really focusing on the Snowflake kind of productionalization of the machine learning model, not necessarily the actual data science code. But you can see we're dropping many of these features. Here's the data that we're going to be working with. So we have the fare, the class, if it's a man or woman, where they embarked from, if they have any siblings or spouse, or sibling or parent, I believe is what this means, and parent and any parents or children on the boat. I hope this data set is not triggering for anybody. I know it was only 100 years ago, so maybe too soon, but I hope you can, have some patience. So usually, like this is saying here, usually the data would already be in Snowflake. This shows us how to write the pandas data frame as a table and then turn the table that's already in Snowflake into a pandas data frame in memory. So what we're doing here is we create a Snowpark data frame. We then write it as a table called Titanic Raw. So if we look here in our databases, in our learning database, we should have a table called Titanic Raw. Yeah, see, we just created that. And it's got 890 rows. So this cell is what created that table. Oops. All right. Now what we can do, right here we're reading a table from Snowflake into a Snowpark data frame, which is what's happening right here, and then we're actually turning it into a pandas data frame so that it's completely in memory on this cloud compute instance, on this container runtime. So now we have Titanic Raw. We can run select all on Titanic Raw and show that query. And so Snowflake notebooks are really cool because you're able to execute SQL and Python all next to each other, and you can actually pass as variables the output of a SQL query or the output of a Python cell execution. Here we are running pandas.head by converting it to pandas as well. Here we're dropping any NAs, we're getting dummies. We're also dropping survived we're creating our X and our Y variables. Y is only the survived column and then X is everything else. We do our train test split with a random state. We're also going to be doing a grid search here, so we set our parameter grid. And by no means I'm saying that these are the perfect numbers and that I'm a data science expert, nothing like that. This is just what has been specified. It's more just to conceptually show that this can be done with Snowflake. We then specify the model, so we're saying XGBoost classifier with binary logistic objective, eval metric of log loss, set our grid search object, pass in our parameter grid, and then we run the grid search.fit method. Here we're extracting our best parameters and best score, so we see that all of the, out of all of the models that we trained with our grid search, the best one had 0.82, what was that, accuracy? Yeah. Maybe accuracy, maybe precision, I can't remember right now. Okay, here we go. Yeah. Accuracy of 0.82. There we go. Metrics. Best score, best params. Yeah. Awesome. So awesome. We've trained where we did a grid search to find the best model for this use case. Or with the limited parameters and limited data that we had. So now it comes to actually productionalizing. Let's take a step back and look at what we've done so far. So we just completed step 1. We have trained the model and it is sitting as a XGBoost object within our compute instance. We now need to actually load it into the model registry so that it can be referenced and productionalized further on. So that's what we're doing here. We are getting a sample data set, just grabbing a small piece of what we trained the model on. We create a registry object that we will work with in the future. Later on in this cell, we specify the name of the model, and then we run registry.log model. So here's where we're able to say, okay, here's the model name. Here is how we plan to invoke this model. So you can also specify here, you could say, I believe it is Snowpark container services. I might be wrong on that. The exact syntax might be different, but you put something here to indicate I want to both be able to execute this using a Snowflake warehouse for like batch inferencing, or using a container instance for live inference, online inferencing. We then specify the actual model, give it some sample input data, and then the metrics associated with it. So that's the good thing about model registry, and I think I've touched on this before, is that you're able to look at your models, your different model versions, promote them to production, like scale or roll them back off of production. You have some metrics about accuracy and things like that. There are also a lot more robust features of ML monitoring that have recently come out through Snowflake. So again, that's another video that I could make in the future, but definitely something to check out. Let's take a look at the Database Explorer real quick and look at the actual model registry object. So if we go to AI and ML, models, we can see the Titanic model has been loaded in here. And within this, we can see the different versions we have. We can, like I said, we can create model monitors to keep track of model quality. So that'll track accuracy and rock AUC, I believe. You can track that. Obviously, you'll have to bring in more data and have kind of some ground truth that you're measuring against, right? Within the version, we can see associated information like the training framework, the different aliases that it has. So you can create your own custom aliases. These are the ones that are given by Snowflake by default. You could create an alias called prod or test or most recent, things like that. We can see the runtime it was created with. Again, those accuracy and training parameters metrics that we had talked about before. And then you can see the different functions that you can run. So this is a newer function within Snowflake that is built in, the explain function. I believe this uses Shapley or Shapley values to indicate which features had the most significance on the model output or on how the model is weighted, you could say. And then predict is giving the score. Are they going to, in this case for the Titanic, did they survive or did they not survive? Or do we predict that they would survive or not survive? And then predict proba pretty much breaks that prediction, that binary prediction. You're able to see the actual probability of them surviving and the probability of them not surviving. So if it predicted for them to survive, that might be 0.91% survival chance, and then 0.09%, 91% chance of survival versus 9% chance of not surviving. And so it gives you a little more visibility into how the model made those decisions. So that's the information available through the UI in model registry. But coming back to the notebook, we can see that the model was logged successfully. We saw that through the UI, obviously. There are a couple of warnings here. Here we're looking at some of that same information that's exposed through the UI. We're calling that, or we're accessing that information through Python here. So we're saying registry show models. We're accessing the model name. And we can see that we have a lot of the same information that we could see through the UI. We can see the different versions, different aliases. We can do the same thing here with looking at the specific versions of our Titanic model. We can see the different aliases of this specific version. Again, more information about what functions are available, the accuracy metrics. We can also access the most recent model of that model name, of that model instance, you could say. We can change the default version. So when the model is called and a prediction is made, it will use the default version usually. And so we can specify to make the most recent version the default version. And then here's where we're actually running an inference, you could say. So we're saying model version, which accesses the Titanic model and the most recent version. We then say run, and we need to pass in a data set and then specify a function name. So in this case, we're passing in xtest, pandas data frame that we specified earlier, and then we are accessing the predict_proba function name. And then that prediction is saved to this data frame, and then we just run .head, which shows us, we're not actually looking at the input features, just the outputs. And so we can see this person had an 89% chance of surviving and a 10% chance of not surviving, and so on. So this is what the output of predict_proba looks like. Predict would be just a single column, either a 1 or a 0, if they survived or not. Here we are writing the test pandas data frame to a Snowflake or a Snowpark data frame, and we're writing it as a table into Snowflake. So we're creating a data frame off of xtest. We save it as a table called Titanic Predict, and then we access that table through Snowpark and say .show. And so now we can see these are all the input features, and then we're going to actually run a prediction on it. So in this case, this is SQL code here, and this is showing how we call the model using SQL. All we do is specify the model name, and then exclamation point says, okay, I'm going to call a specific function off of this model. So in our case, we're running the predict_proba function. We then pass into that function all the necessary input features, and that's going to load in the model into the compute instance, into the virtual warehouse, and then run all those predictions in parallel, so kind of a batch parallelized prediction job, and create those output predictions. And then what we're doing here is, this is Snowflake's dot notation to access elements of a JSON object, and so we're accessing the output feature the output feature key of the key value pair that is produced by this function. And so then we are rounding that to 2 decimal points, and we're calling it survival prediction. So in this case, this person who paid $13, I believe, $13, and was in second class, was a woman who embarked from Southampton. She had a 92% chance of survival. So great for her. That's good. So this just shows how simple it is to create a prediction using a saved machine learning model in the model registry. Now we're going to deploy this in a repeatable way that will incrementally create predictions as new data comes into the system. And so it's super simple. All we do to create this pipeline, you could say, is create a dynamic table. So we're calling it Titanic Batch Inference, and we just specify create or replace dynamic table. We give it a target lag of 1 minute. So every 1 minute, the system will check if any new data has come into the underlying data set, which is, in our case, we're selecting from Titanic Predict. So if a new record comes in, then after a minute, the system will check and see that new record and say, okay, we need to run this through this SQL query, and then populate that into the dynamic table, and so a prediction will be made off of the model. Obviously, that takes some compute to check the underlying data set for new records and then also make the prediction. And so we specify a warehouse here. This is cool. This demonstrates that we can use variables from Python in our SQL query. That's kind of one of the cool features available in Snowflake notebooks. And so we're saying current warehouse. We're specifying that in the Python cell, and then we're utilizing that variable here in the SQL call. And then the way that we're or the transformation that you could say is happening in this dynamic table is this SQL call right here. And so all we're doing in our case is selecting everything from the underlying table, which is Titanic Predict, and then running that same prediction logic here. So the model is being accessed, running this function, accessing the output, and rounding it to 2 decimal places. And then in this query, we're just selecting from that dynamic table. Cool thing about dynamic tables is that it's fully managed. You don't have to create any code to trigger them. It's all kind of in this one SQL call. You can also set the target lag to downstream. So let's say you chained a couple of different dynamic tables together. and you set them all to downstream lag except the very last one, you could change that last one that draws from all these different dynamic tables to 5 minutes or to 1 hour or whatever. Anytime you change the lag of that one table, it will make it so that every other table upstream, up that chain, will change to only refresh at that set interval. And so why that's important or why that's good is because let's say that your reporting mechanism or your dashboard, whatever it is only drawing off of that last dynamic table in the chain. And you decide, okay, we don't actually need to refresh this data every 5 minutes. People only look at it once every 4 hours or 3 hours or something. And so you could change it from 5 minutes to 1 hour, thereby saving you compute cost because you're not refreshing as often. But your end users still get fresh data every time they use it. And so setting that chain of dynamic tables to downstream makes it so that you only have to change one number in one spot, and everything up the line will be modified to accommodate that. And so saving you money, getting you fresh data when you need it, but also not paying for overly fresh data, you could say. So that's a really cool thing about dynamic tables. Okay, so now we can see our dynamic table has been created. We can see that there are 287 records. Now, if we run an insert, we've inserted 20 more records. And let's actually take a look at this in the UI. So if we go to dynamic tables, we go to Titanic batch inference, we can look at the refresh history. And we can see that 287 rows were added when we created this dynamic table. You can see I created it a second ago, and then I deleted it, and then I added some rows. So that's what you're seeing here. But we can see here I added in 20 additional rows, and so it took 10 seconds to refresh. What's this we're seeing? Refresh lag exceeded the target lag. So in this case, the target lag is 1 minute. In our case, it took 1 minute and 2 seconds. So this is relatively low target lag. And as your dynamic table lives and as you are, as the system does these refreshes, it'll learn how long it usually takes, how long this refresh duration takes. And so if it takes 30 seconds and your target lag is 1 minute, it'll know to kick off that refresh with 30 seconds left or something like that. And I mean, in that case, those are, that's kind of a special case where the refresh duration is almost half of the target lag. That's not typically something that you'd want to aim for. I think, you typically want the refresh duration to be a lot shorter than your target lag. But so that's what this triangle is here. But we can see that 20 rows were added. The refresh action was incremental, so we only paid for those additional records that were added. We didn't pay to recreate the entire table. And then we can see, I guess we can't look at it here, but those additional 20 records were added to the end of this table. Well, let's look at in the notebook. If we run this select all, we can see. Come on. Yeah, 307 rows, each with their own prediction of survival or not. So this just goes to show that it's extremely easy to deploy a machine learning model in Snowflake using dynamic tables so that you can incrementally run these batch refresh jobs. If you have any more questions about this, please reach out. Also, if you want to see more specific features of Snowflake machine learning, how to operationalize your machine learning models in Snowflake, please offer your suggestions in the comments. I love the engagement that I'm getting in the comments, so keep that coming. And yeah, good luck with this project. Good luck deploying your machine learning models in Snowflake with dynamic tables. Super powerful, super simple. So enjoy.